Okay, so I'm going to talk to you for a few minutes about graphing. Um, the most common mistake I think a lot of students make on this is they assume it's going to be easier than it really is because you probably had to draw graphs in the eighth grade or somewhere like that, and you think, well, that's easy, no big deal. But it's going to be a little bit more rigorous, more quantitative. And has to be done a little more professionally than what you might have been expected to do before, or maybe not. But anyway, here it is. So let's say you have several points drawn on some axes here, velocity versus time. Um, this would be this would come from somewhere like, say, for example, if somebody did some kind of an experiment like we might typically do in lab, and they got a bunch of data values of velocity and time, all right, and then they plot them on this graph. So these are real experimental values. Let's say the experiment was such that the acceleration was actually constant, okay? So when acceleration is constant, you expect velocity versus time to be a straight line. All right. Now you look at these and you say, well, if I ignore that one outlier down there and just focus on the others, they're sort of a straight line, a little bit, close to a straight line. Well, that's because of experimental errors. They may not form exactly a straight line, but they may come close to forming a straight line. Okay. Okay, now you might want to take a look if your eyes wandered a bit. Now this picture includes a couple of things it didn't include a second ago. I've drawn a line through those points now, all right? And I've also written an equation down there where it says V equals VO plus A times T, all right? So what's going on here is somebody did an experiment where they got some data, velocity versus time, and they're going to assume that the acceleration was constant in that experiment. Or it might not be just a casual assumption. Maybe they have good reason to really know that the acceleration was constant. But in any event, the data should fall along a straight line. When you have constant acceleration, that's what's supposed to happen. All right. So we're trying to fit the data to a line. So when I drew this line, I just by eyesight, I just chose a line that to me appeared to fit the data pretty well. About as well as we can get. It doesn't go through all the data points, but that's because there's some error in some of the data points. But they're not that far off, except for that one outlier down there. We'll deal with that. But the others are not that far off. So that's the best line we can get, or at least a good line that fairly well fits the data. All right, that's the idea. The human eye is a pretty good estimator of that. Okay, now you notice that one lonesome point down there by itself. I just didn't choose that, or I omitted it. Now that may sound like cheating, okay? And it can be cheating if you do too many like that, but if you're doing something like this and you have one data point that clearly doesn't fit all the rest, then you might reasonably say, okay, something went wrong with the apparatus when that data item was collected. Maybe somebody wrote a value down wrong or something like that. Clearly there's something wrong with that point. So we're going to take the liberty of discarding it. Okay, so sometimes if you're very careful, it's okay to do that. All right. Okay, so the idea is I've drawn this line and I can get a slope and an intercept of it. You probably already know how to do those. Maybe not the best way, but you probably know how to do them. Okay, so I can take a couple of points and get a slope and an intercept. Okay. Okay, now take a look again and you'll see even a couple of more items added. Now I'm taking a slope. So you see the delta y and the delta x there. All right. And then if you look at the y-axis, you'll see the intercept there. I don't know how well it shows up in video, but that point right on the y-axis is supposed to be in red or pink. Okay. It's different. It's not an original data point. It's a point that I drew to indicate where the line hits the y-axis, or the velocity axis, I could say. So when I find this slope, that actually should be equal to acceleration. That's the constant that's in front of the x term, all right? And then the intercept actually in this case would be equal to the initial velocity, the VO. Now in the problems you do, it's going to be the same idea, but there's a little bit more work to it because the formulas you have some extra terms in them, and you have to do a little bit of unraveling to find out that the slope might not be equal exactly to the one thing that you're trying to, the one quantity you're looking for. You might have to do a little bit other algebra to figure it out. But anyway, that's the idea, okay? For example, in this graph, the idea would be we would like to know what acceleration was in this experiment, and we'd like to know what initial velocity is. And maybe we didn't have the means to be able to measure those things, but from the data, velocity versus time, we can get it this way, or at least an estimate that we're pretty confident in. So that's the idea, all right? Now, you have probably seen this kind of stuff before, but a few rules, though, that you have to obey when you're doing it in here, because we're trying to teach you not just to draw a graph and do slope and intercept and so on, but how to do it in a very scientific and precise way. So when you get the slope, you're going to notice if you look at that line that I chose a couple of points to use as a slope that are actually not original data points, but they're from the line that I drew, all right? That's actually better because they come from the line that you've drawn and not original data points. That might seem a little backwards at first, but the idea is you want to represent the line, not necessarily, well, you want to represent the line that characterizes all of the data on average, okay? So that's why you take it that way, all right? And the y-intercept, you just read directly off the graph. Sometimes people want to take a data point and plug in the formula and find it there somehow. Actually, it's better to just read it directly from the graph. That's a good way to do it. Okay, that's how we want you to do it. All right. Also, it's no accident on the slope that I chose a couple of points that are kind of far apart, and that makes it more accurate. You want to do that. All right. There's always going to be some uncertainty in reading a value from a graph, but if your 2 points are far apart, your delta y and your delta x are bigger, and so proportionately the uncertainty won't be as big of a fraction of your delta y and delta x, so you get a more accurate slope this way. All right, so that's the idea on that. All right. Okay, now take a look again and you'll see something else. You'll see that pink line there. This is an example of a bad way to do a line, okay, or a slope actually. Some people would be tempted, it might seem tempting to think that using original data points with all the decimal places is somehow going to be more accurate when you're finding a slope or something, or an intercept or something. The pink line shows what if I took those 2 points. You notice it goes through 2 of the points. If I were to take those 2 points and plug them in to use those to find a slope, well, if I did that, I would essentially be getting a slope of that pink line, all right? That's what I would be getting. And you see from there pretty clearly, it's pretty easy to see visually that that line is actually sloped quite a bit differently than the line that represents all the points, all right? So that's why you don't necessarily just take 2 original data points and find a slope. You want to pick a couple of points on the best fit line that you draw, all right? Okay, now I've gone back and erased that bad pink line that was the wrong way to do a slope. Okay, so just a couple of more rules. You're going to notice on this graph that on the axes, I actually wrote out time, seconds, and velocity, meter per seconds, okay? So you always want to write the full name of the variable that you're graphing and also the unit, okay? So that way, when you look at the graph right away, you know what I mean. You know I mean time If I just abbreviated it with a T, you might think it means torque or tension or something like that. But this way, there's no mistaking time is what what the x-axis is, and then seconds. So you don't have to guess at what the unit is. Otherwise you might think it's minutes or hours or something. Okay. The idea behind that, it may sound a little nitpicky, but we're trying to get you into the habit of fully reporting things. So if you were doing a graph in a report or a research paper or a report you might have to do for your boss someday, well, you don't want them to have to dig for the information that they need. If you got it all right there where there's no mistaking it, that's the best way to do it. All right. So, and also when you draw a graph on graph paper, you want to make it big, as big as you possibly can, but yet keeping a good scale. So whenever you're drawing a graph, you always choose a scale, like every centimeter block on the graph paper is going to represent 1 second or 2 seconds or 5 seconds or something like that. So you choose a scale so that the graph turns out to be pretty big, taking up most of the room of the graph paper. The bigger it is, the more accurate your slope and intercept are. That's why we do that. All right. So you want to make it big. You don't want to make it just small when you could possibly make it bigger. Now, having said that, I should also say that when you choose a scale, choose a number that's easy to work with. Like, say, if you were choosing your time axis scale, make 1 centimeter represent 1 second or 2 seconds or 5 seconds or something like that. I said make it as big as you can, but don't make your scale something like every centimeter means 0.762 seconds or something like that, just to make the graph as big as possible. So you've got two constraints. You've got to make the scale something that's a nice number that's easy to work with, so somebody can look at it, and if they want to read something off your graph, they can do it more easily. But also make the graph reasonably big, about as much of the graph paper as you can get, and also have a reasonable scale. So that's the deal on that. All right. So anyway, just to summarize really quickly, there's a lot of rules. There's a lot of information here. Make the graph as big as possible, full words. It can include units on everything. Graph paper, it might sound a little obvious, but yes, use graph paper. If you draw this on notebook paper and just think you're measuring it out, it's not going to be nearly as accurate. So that's really not good at all. Never do that. Okay, use graph paper. Even if you don't have some of the kind we gave you, if you have some other rectangular grid graph paper, that's okay. All right. Slope points far apart. Use points on the line, not original data points. Use points on the line that you drew. Okay. And the intercept, just read it directly from the graph. Don't try to calculate it some way. That's actually the best way because it comes from the fit of the data. Okay, I'll let you get to it.